I'm Evan,
I'm Tyler.
and today we're going to be talking about dams and hydroelectric power and how it relates to physics. Let's start with an introduction. Dams are important because they're a relatively clean and renewable source of energy. They generate 16% of global energy, and they used to be the main source of renewable energy until very recently. How do they use physics? They rely on mostly fluid dynamics, and they use Bernoulli's equation and the hydrostatic equation. Let's get into it.
Before we actually talk about the physics of dams, let's actually get into a little bit about the machinery behind the generation of electricity. The generator itself is composed of four main components. We have the turbine, which is the contact with water. We have the shaft, which is connected between the turbine and the rotor, and this spins both the turbine and the rotor. We have the rotor, which produces a magnetic field, and we also have the stator, which generates the electricity.
Let's get into the physics. The hydrostatic equation is crucial for generating a higher pressure in the penstock. Dams are built around natural drops, or they create elevated reservoirs that create a height difference between the resting water and the turbine. So here we can see a general outline of a hydroelectric dam. We have an initial pressure at the reservoir, and then a height difference between this pressure and the pressure at the intake point. This creates a new pressure in the penstock that is higher than the initial pressure. Next, let's work in Bernoulli's equation. Bernoulli's equation is based on the concept that the flow rate in is equal to the flow rate out. This means that the pressure at one point plus its velocity and its height is constant and will be equal to the sum of those components at another point. Here we can see the same diagram. We still have an initial pressure at the reservoir that is higher in the penstock because of the height difference. Now notice also that the penstock is thinner. Based on Bernoulli's equation, we know that because this is thinner, the velocity of the water will also be faster than it is at the top of the reservoir. This increased velocity, along with the increased pressure in the penstock, is what moves the turbine and generates electricity.
Now let's get into a little bit more about the electricity generation of dams. So now we understand that the generation of electricity occurs from differences in flow rate and differences in pressures. But how is this difference in flow rate and pressure actually transferred into usable electricity? Let's go over the four main components of the dam generator one more time before we get into the main mechanism. We have the turbine, the shaft, the rotor, and the stator. Initially, the flow of water generates kinetic energy. When this kinetic energy meets up with the turbine, the kinetic energy is transferred into mechanical energy through the rotation of the turbine. Second off, the rotation of the turbine rotates the shaft. The shaft, in turn, is connected to the rotor. Therefore, when the turbine turns, the rotor itself also turns. The rotor is packed with many magnets, and the rotation of these magnets helps to create a magnetic field. This magnetic field is very similar to the type that we see on Earth. As the rotor spins, it passes by copper coils that make up the stator. When it passes by these copper coils, electricity is generated.
Next up, some dam fun facts. Firstly, the Three Gorges Dam in China is the largest dam in the world. It can generate up to 22,500 megawatts of electricity. It's 181 meters tall, 2,335 meters wide, and the reservoir it creates is 1,045 square meters.
Next up, the oldest dam in recorded history was built in 2900 BC, approximately. It was built along the Nile River and was used to supply the people of Egypt with water and not to generate electricity. Finally, an alternative usage of dams is to actually irrigate crops. This is due to the fact that it helps to stabilize water flow.
The end. Thank you.